Hello everyone. Our topic for today's presentation is AI-based speech emotion recognition using LSTM and BiLSTM. The motivation behind this project is rooted in the gap that exists in speech recognition system today. While they can transcribe what we say, they often fail to understand how we say it. This emotional gap limits their effectiveness in areas like healthcare, education, customer support, and virtual assistant. Our goal is to build a deep learning model that can classify emotions from speech. We focus on 7 emotions and aim to establish baseline model that will guide future improvements. The dataset source is Toronto Emotional Speech Set. It contains 2,800 audio recordings from 2 female speakers covering 7 emotions. We chose TESS because of its high quality recordings, consistent labeling, and strong reputation in emotion recognition research. Our input for this data set is we are extracting MFCC features from it, and this is because it is commonly used to capture characteristics of human voice. The output is a predicted emotional label. This is a classic multi-class classification task with 7 possible outcomes. For example, from one audio clip, the model might predict happy. The methodology we followed is we began by performing exploratory data analysis on the dataset to understand its characteristics. We performed some data augmentation to understand if the augmentation has some impact on the data. We extracted MFCC features from the audio files. We then visualized the data using waveform, spectrogram, samples, and MFCC heat maps. We split the data into 80% training set and 20% testing set and trained LSTM and BiLSTM models. We used accuracy, confusion metrics, and classification reports, precisions, and to understand the model performance.
Exploratory data analysis. From our EDA, we found out that MFCC features are effective for capturing speech tone variation across different emotions. Notably, pleasant surprise and happy have similar MFCC features, which was considered during training to avoid any overlaps. The short duration of the audio samples of around 1 to 2 seconds is suitable for low latency, real time emotion prediction, making this dataset ideal for practical applications. The baseline neural network model that we implemented was LSTM. We first, which is effective for sequential data like speech. LSTM layer with 256 units to capture temporal dependencies, dense layer to reduce the dimensionality, and dropout layers to prevent overfitting. We used a stochastic gradient descent optimizer here with 150 epochs and a batch size of 64. The model algorithm for LSTM, we plotted the graphs for accuracy versus epoch, which shows the improvement in model accuracy over time, and loss versus epoch plot shows the reduction in loss, which indicates the model is learning effectively. The next model was the BiLSTM, which captures both past and future dependencies in the sequence, making it specially powerful for speech emotion recognition. Bidirectional LSTM with 256 units to capture both forward and backward temporal dependencies and dense layer to reduce dimensionality. We used Adam Optimizer for this one and trained for 300 epochs with a batch size of 64. Similar to LSTM, we plotted the accuracy versus epoch and loss versus epoch plots indicate that BiLSTM outperforms LSTM in terms of both accuracy and loss reduction, showing better generalization for emotion classification.
To optimize our models, we use dropout layers, which were added after LSTM, and dense layers to prevent overfitting. The Adam optimizer is an efficient variant of gradient descent that adapts learning rates. The validation split, we held out 20% of the training data to monitor overfitting and ensure that we have model generalization. Now, for epoch training, the BiLSTM model was trained for 300 epochs, ensuring convergence and stable performance. We used several evaluation metrics like accuracy versus epoch plot, which showed the accuracy improvement over time, loss versus epoch plot, which helps identify if the model is overfitting or converging, the confusion matrix, which provides a detailed insight into which emotions were predicted correctly or misclassified. Classification report includes precision, recall, and F1 score for each emotion class, allowing us to see how well the model performs across different emotions. Here are the classification reports for LSTM. And on the next page, this is by LSTM models. So the reports show precision, recall, and F1 scores for each emotion class, providing a detailed breakdown of performance. Key takeaways. So while LSTM provides a solid baseline, BiLSTM shows clear improvements in both accuracy and consistency, especially in recognizing emotions requiring nuanced temporal understanding. The confusion matrix and other evaluation metrics indicate that BiLSTM performs slightly better, making it preferred choice for emotion recognition in speech. None of the team members had prior experience working specifically on speech emotion recognition. However, we leveraged our experience in audio preprocessing, deep learning with LSTM models, and time series analysis to successfully implement this project. Here is a list of our references. Thank you so much.